Hello and welcome to this video on expressing a system of linear equations as a linear combination of vectors. So in this video I have just several examples of systems of linear equations, and we're going to be solving them. But first we're going to be expressing them in a different way than you probably are used to. I'll first show you like the rewriting it as a matrix equation, right? A matrix product on one side equals some matrix on the other, and then getting to the heart of the section, the heart of the video, on rewriting it as a linear combination. Okay. So to begin, I got my first example here is this two equation, two variable system. As to express the system of linear equations as a linear combination of vectors. So I have x1 plus x2 equals 3, x1 minus x2 equals negative 1. And again, this could be x plus y, x minus y. If you want to replace x1 and x2 with x and y, it's fine. Alright, so something you're probably familiar with is rewriting a system as a matrix equation. Right, where I think of each side of the equal signs as in this case it would be a 2-row by 1-column. Think of this as a 2 by 1 matrix here, right? This 3, negative 1 column vector. And think of this entire side as a 2 by 1 matrix, and then break it up into a product of a coefficient matrix and a variable matrix. All right, so and I have a coefficient matrix where down one column goes the coefficients of x1, so 1 then 1. Then down the second column goes the coefficients of x2, so 1 then negative 1. Right, there's the coefficient matrix, and it's a 2 by 2, right? And if I would like the resulting product to be equal to a 2 by 1, I need to multiply it by a 2 by 1 matrix, right? So here's a 2 by 1 matrix with the variables in the order that I wrote the coefficients in, right? These are the coefficients of x1. So in the first column, so the first entry here should be x1, and these are the coefficients of x2, so the second entry here should be x2. And if you were to take the product of these two matrices, right, this 2 by 2 times this 2 by 1, you would get the 2 by 1 matrix. That's this left side, right? Again, if you thought about it as a 2 by 1 matrix. And then this is equal to the 2 by 1 matrix on the other side, the column vector with components of 3 and negative 1. Okay. So again, most people are familiar with this, rewriting a system of equations this way as a matrix equation. Coefficient matrix times variable matrix equals constant matrix. But what we're asked to do here, and what we're trying to do here, is express the system as a linear combination of vectors. So again, I'm going to, just as I mentioned before, we're going to think of the left side and right side as 2 by 1 matrices. So on the left side I have this x1 plus x2 and x1 minus x2 are the components of the 2 by 1 matrix on the left side, and that should be equal to the 2 by 1 matrix on the right side with these components of 3 and negative 1. Right. Now recall that I put up a video before about linear combinations. Remember, a linear combination of vectors is the sum of several, of scalar multiples of a group of vectors. And so what I'm going to do here is I'm going to break this left side with the variables up into a linear combination, a sum of scalar multiples of some vectors. And what I'm going to do is just split it apart using the x1 terms and x2 terms, using like terms. So splitting this apart, this is equivalent to the 2 by 1, it's a 2 by 1 matrix, and I'm going to break it apart using, vector addition. And when you're adding vectors, right, they have to have the same size. So in order to have a 2 by 1 matrix be split into a sum, you're going to have to split it into the sum of other 2 by 1 matrices. So one with the x1 terms, x1 in the top component, x1 in the bottom component. So this is the vector x1, x1 plus, right, and then the vector composed of the x2 terms, x2 in the top component, and then negative x2 in the bottom component. All right, and this is equal to, again, the vector 3, negative 1, right, the 2 by 1 matrix. And again, you have 2 by 1 plus 2 by 1 equals 2 by 1. So the requirements for vector addition, matrix addition to happen still hold. All right, and then one more thing to get this linear combination look I'm asking for is to notice now that, hey, in this first matrix, both components are multiplied by x1. Right? They both have this common factor of x1. So I'm going to pull that out as a scalar. So I have x1 times the vector, and then 1, 1. Right? x1 times 1, 1 would be x1, x1, right? Using the properties. What does it mean to do a scalar multiple of a matrix? Right? You multiply every component by that scalar, and x1 here is a scalar, a real number. All right, then plus, and then same thing here. I noticed that in this second matrix, all components have a factor of x2. So I pull out the scalar, the real number x2, times, and then the vector 1, negative 1, and this is equal to, again, this vector 3, negative 1 here. All right. So here it is, the linear. This is the vector 3, 1, 3, negative 1. Sorry. All right. This is the vector 3, negative 1 as a linear combination of the vectors 1, 1 and 1, negative 1. Okay, so this is going to happen for any system of linear equations. You can write it as either a matrix equation like this, where you have your coefficient matrix times the variable matrix equals the constant matrix. You can always set this up, or you could set it up this way, where the constant matrix. So you'll see that solving a system like this, setting up a system of equations, solving a system, is equivalent to saying that the constant matrix you're trying to figure out, can the constant matrix, right? Can the constant matrix be expressed as a linear combination of the columns of the coefficient matrix? So can the constant matrix be expressed as a linear combination of the columns, right? See, I had 1, 1 here and 1, negative 1. Those are the columns of the coefficient matrix. So solving a system of equations is equivalent to asking this question. Right? So when I see this, another question I could ask is, can 3, negative 1 be written as a linear combination of 1, 1 and 1, negative 1, right? Because if it can, that means I can find values of x1 and x2 that make this true and make this statement true down here, right? So 3, negative 1 can be written as a linear combination of 1, 1, and 1, negative 1. And another term that comes up to these scalars, right? The x1 and the x2, the scalar multiples of these vectors. The x1 and x2, the coefficients of the vectors are referred to as the weights quite often of the linear combination. All right. So the weights you could write as this vector up here, right? This variable vector, the vector with x1, x2, right? So the weights of the linear combination are just are the solution of the system. Right? So lots of stuff, right? Lots of equivalencies here. Lots of things that mean the same thing, right? This system's the same as this matrix equation. This system's the same as this linear combination. The solution of this system is this variable column vector here, this variable matrix, or the weights of the linear combination, right? All these mean the same thing. They're referring to the same system of equations. Okay, so now let's let's solve. Now you've seen, again, most of you hopefully by now are familiar with how to solve a system of equations in multiple ways. You can use Gaussian elimination, Gauss-Jordan elimination. If it's just a simple two variable system here, you could use substitution, elimination methods. But I'm going to be consistent here and use Gauss-Jordan elimination, where, remember, solving this system. All right, so let's solve it now. I'm going to solve it using the augmented matrix. All right, I'll write that here. This is the augmented matrix for the system. Right. Coefficients of x1, it's just basically the coefficient matrix on one side and then a bar for the equal sign, and then the constant matrix on the other side without the variables. Coefficients of x1, coefficients of x2, little bar where the equal signs would go, and then the constant 3, negative 1. Right. Now I know that this is really simple to put in reduced echelon form or reduced row echelon form using elementary row operations. So I'll do those here, and then I'm going to go to the calculator and show you, off to the side there. I'm going to go to the calculator and show you how to do this on the calculator as well, and then I'll be using the calculator for the rest of the video. All right. So for this first one, the first operations I'll use, I like having that 1 in the upper left-hand corner, but you need zeros below and above the leading ones when you're in reduced echelon form or reduced row echelon form. So I'm going to, one of the operations you can do is take a multiple of one row, add it to another row, and replace that second row. So I'm going to take the in order to make this a 0, I need to take the opposite, negative 1 times row 1. Then I'm going to add this to row 2, and this will yield a new row 2. All right. So the first row is not changing. And when I do this operation, take negative 1 times row 1. So negative 1 times 1 is negative 1, plus 1 is 0. That gives me a new row 2 entry. And then negative 1 plus negative 1 is negative 2. And then negative 3 plus negative 1 is negative 4. All right, now I know you can probably already see that x2 needs to be 2. All right, and then you could do back substitution here. But I'm going to continue on and put this in reduced echelon form, right, or reduced row echelon form, RREF, you might see it abbreviated. All right, so here I have a lead 1, step down, there's 0 below, and the lead term in the next row I want to be a 1 as well. All right, so I'm going to multiply the second row by negative 1/2 to get that lead term, non-zero term, to be a 1. So negative 1/2 times row 2 will yield me a new row 2. Okay, so the first row is still not changing. And then multiplying the second row entries by -1/2, you'll have 0, 1, and 2. Right. Okay, and then finally, one more step here, right? I got lead 1, a lead 1 here. I would like a 0 above that lead 1 in row 2 now to get it in, reduced echelon form. So the final operation to put it in reduced echelon form or reduced row echelon form, I'm going to, I would need to multiply this by -1 and then add it to this to make that 0. So -1 times row 2, add those entries to row 1 to give me new row 1 entries. All right, so row 2 is not changing. Okay. Row 2 isn't changing. So it's still 0, 1, 2. It's row 1, that is. Now that's still a 1, -1 times 0 is 0, plus 1 is still 1. Then -1 plus 1 is 0. And then -2 plus 3 is 1. All right. So this leads me to the solutions, right? Remember, these are the coefficients of x1, these are the coefficients of x2, and these are constants with a little equal sign. So that first row corresponds to x1 equals 1. And that second row corresponds to, just 1x2 equals to x2 equals 2, right? And here are going to be the weights. Now this is the solution of the system, right? This is the solution of the system, sure, but it's also, these are also the weights of the linear combination. Okay, so don't forget that. And going back to the way I wrote it, right, here is the original system. And double check your answers, of course. Let's test these out. 1 plus 2 is 3. 1 minus 2 is -1. So these are actually working, right? Makes the system, true, both equations true. But I want to go to here with this linear combination business, So the answer to this question, can the constant matrix, can 3, -1, be expressed as a linear combination of the columns of the coefficient matrix, right? The 1, 1, and 1, -1. The answer to that is yes, right? Because I found a solution. If you don't find a solution, then the answer is no, and you can't finish it off. All right, and then you're seeing here's how 3, -1 can be written as a linear combination of 1, 1, and 1, -1. So replacing x1 with 1, I get 1, 1 plus, and then replacing x2 with 2, 2 times the vector 1, -1 should give me the vector, 3, -1, the constants on the other side. Right. And let's just, again, double check this. 1 plus 2 is 3, 1 plus -2 is -1. Check. So here you go. All right, this is 3, -1 written as a linear combination of the vectors 1, 1 and 1, -1, right? It's a scalar multiple of 1, 1 plus a scalar multiple of 1, -1. Great. All right, now I'd also like to show you on the calculator, remember this augmented matrix I had up here, how to put it into, this is that reduced row echelon form or just reduced echelon form here. RREF, right, this guy with the leading ones in every row. The first non-zero entry in every row is a 1, and then below and above those ones are zeros. So on the calculator, if you go to the matrix, I have a TI-84 plus, right? If you have an 83 or 84, this is similar. Go to the matrix menu, go over to edit, and then I'll say let's enter matrix A here. Now this is a, this was a 2-row, 3-column matrix, right? So it's a 2 by 3 matrix, so 2 by 3, and then you get these entries to enter. The first row had 1, 1, and 3. So then the next one had 1, -1, and -1. Okay, so I've got the entries in here now. Let's get out of this. So quit. And then if I want to put it into this reduced row echelon form, right, RREF, I go to second on the main calculation screen, go to matrix menu again, over to math, and then I'm going to hit up because it's pretty far down. There's, down here at B, there's RREF. There's actually also REF, all right, pay attention, be careful, you know which one's which. REF is row echelon form, or just simply echelon form, not reduced, right? So let's go down here to RREF, that's reduced row echelon form, or what you might know as reduced echelon form. So I hit enter, that comes up on the screen, and then it says, hey, what matrix would you like to put into reduced row echelon form? Go back to the matrix menu, and then under names, I have the 2 by 3 matrix A that I put in earlier. Enter there, close parentheses, and then there you have it. And can you see how, there's, 1, 0, 1 first row, 0, 1, 2 second row, exactly what I have here after doing the row operations that I did earlier, right, using, doing Gauss-Jordan elimination. All right, so that's what I'm going to do the rest of this video, is using the calculator, because it can get a bit tedious. Maybe some examples where there's just 2 equations, I'll do a row operation or whatever, because it might be pretty quick. But when there's 3 equations, 4 equations, doing the row operations can be a bit tedious, and I don't want to waste too much time in the video. It's already going to be long enough as it is. All right, so let's get to another one. All right. So my next example is another two-equation, two-variable system. All right. And remember this, I'll start off all these, you can write these as a matrix equation. Let's write matrix here, where the coefficients of x1 down one column, coefficients of x2 are look at the same thing down another column, times the variables, right, x1, x2 equals, and then this constant matrix on the other side of the equal sign, 3, 6. All right, and remember when I said earlier, when you see a system of equations where it's all the variables are on one side, constants on the other like this, you can really ask this question: if this has a solution or not. The question is, can the vector 3, 6 be expressed as a linear combination of the column vectors 1, 2, and 1, 2. Now I know you're thinking, hey, these are the same thing, so it's kind of silly to say both. Because if they're the same vector, really, you don't need to repeat it. So can 3, 6 be expressed as a linear combination of just 1, 2, or basically a scalar multiple of 1, 2? And yeah, if I multiply this by 3, I get this. So I could have 3 of this and 0 of that. All right, 3 of this 1, 2, and none of that 1, 2. Or I could have 1 of this 1, 2, and 2 of that one. As long as I make 3 of them, I'll get this. All right, but that's the question you're asking, though. Every time you can ask that now. Every time you see a system of linear equations, variables on one side, constants on the other, you can ask, can that vector of constants be written as a linear combination of the column vectors, if you look at the coefficient matrix. All right, so if I write this like I did earlier as linear instead of as a matrix equation, write it involving a linear combination, it would be x1 times the column vector with the coefficients of x1, right, 1, 2, plus, and then x2 times the column vector with the coefficients of x2, which is 1, 2 again, equal to the column vector, that's the constants, the 3, 6. All right, so solving this system is the same as solving this matrix equation, and the same as solving this linear combination, right? Finding the weights, finding the x1 and x2. All right, so now I'm going to get to solving. Now this is one where I won't really use the calculator. I know I said I'd do it from here on out, but this one's super simple. Here's the augmented matrix, right? 1, 1, 3, and then 2, 2, 6. Can you see how I would very simply just need to take -2 times the first row and add it to the second row to give me a new second row, and the new second row would simply be a bunch of zeros. 1, 1, 3, and then 0, 0, 0, right? So what we have here is a case where, this is my only pivot column, right? This is the only leading one, and then you have 0 equals 0, which is fine, right? This second row corresponds to 0 equals 0, which is okay, and you can ignore it, right? This is always true. You don't have to worry about it. So the first equation is the only one we're really dealing with. So the pivot, my pivot column is in the column for x1, right? So we would say that x1 is a basic variable, and probably, I'm sure I'll have videos up of this, this stuff at another time. And then this second column doesn't have a leading one in it, right? It has a 1, sure, but it's not the leading one of any row. All right, so x2 is a free, what they call a free variable, right? So I can let x2 be whatever I wish. So very often now you can leave it as x2 if you want, but because x2 is free, I'm going to say let's let x2 be any real number I wish. So I'm going to say let's let x2 be, the letter t, where t is any real number. This happens very often, right, where a free variable is represented by an expression that represents any real number, whether it be t or s or 2t or 5t or a third t, some expression that can take on any real number value. So then this first equation, when I'm in reduced row echelon form here, corresponds to having x1 plus x2. All right, but I'm going to call x2 this number t. I need this number t. I want x2 plus x1 plus t equals 3. Again, you can leave it as x2 if you wish. Totally fine. Equals 3. And then the value of x1 would be 3 minus t. All right, when I solve it for x1. All right, so the solutions of this system, there are infinitely many. Okay, there are infinitely many. So the solutions of the system, right, the x1 and x2, take on the form, 3 minus t and t, where t is anything I want, right? T is any number I wish. Okay, so and like I said, infinitely many solutions. And what you're going to see is that when you have a system with infinitely many solutions, that means at least one of the columns isn't necessary. You'll get into I'll make a video later on the concept of linear dependence and linear independence. What you're going to see is that the column vectors are linearly dependent. So basically, when you see a system with infinitely many solutions, it means at least one of the column vectors isn't necessary, for the linear combination. I'll show you what I mean. And this is a huge thing right here. Again, we'll talk about in another video linear independence versus linear dependence. So going back, right? Look at it. This was the linear combination equation. When I wrote the system as a linear combination. I can have I can have t be 0, right? I'll set that up. Again, t can be any number I want. So if t were 0, we get x1 equals 3, x2 equals 0, and this is what I was talking about. You don't need this second, pardon me, you don't really need this second column. So I'd have 3 times 1, 2 equals, plus 0 times 1, 2 equals 3, 6. And again, double check, make sure this is actually true, right? 3 plus 0 is 3, 6 plus 0 is 6, right? It works out. Yeah. Okay, and again, you could have t be anything you want. I could do other stuff. If t equals, 5 or something, then x1 would be 3 minus 5, so x1 would be negative 2, and x2 would be 5, right, value of t. And then I get this linear combination, replacing, I have negative 2 times 1, 2, plus 5 times 1, 2 equals 3, 6. And again, double check, negative 2 plus 5 is 3, negative 4 plus 10 is 6, works out. All right, but really what you're going to see is that, the second 1, 2 isn't necessary, because you can say these are dependent. You can write 1, 2 as just 1, 2 again. You can combine these to make 3, 1, 2. You can combine these as long as you combine them to make 3 times 1, the vector 1, 2, you get 3, 6. Right? Notice how negative 2 plus 5 is 3. 3 plus 0 is 3. Right? As long as those coefficients, those weights add up to 3. Right? 3 minus t plus t is 3. Right? As long as the sum of the weights is 3, you'll get a good linear combination here. All right. Yeah, I'm not going to really worry about this yet. We'll talk, like I said, there's a future video coming up about linear independence, linear dependence, where you'll determine which vectors are unnecessary. Now, obviously, here, they're the same vectors, so one of them you don't need. All right. In the future, when you have multiple, 3, 4, 5 vectors in a linear combination, and there's dependence, then you can figure out, which you can go into a little process into figuring out which ones are not needed. But like I said, that's a future video. All right. So another one, right? Like I said, this whole video is going to be a bunch of these, right? And we'll build our way up. We'll build up to 3 equations, 4 equations, and so on. No, I don't think I have any with 4 equations. All right. So again, you can write as a matrix equation. Not going to do that this time. I'm just going to go to the linear combination as a linear combination. Linear combo. And we have, again, just you can split this up to the x1 terms. x1 times the vector with its coefficients, 1, 1, plus, and then x2 times, and oh look, it's another one where they're the same. Another 1, 1, right, equals, and then this vector 3, 1. All right, again, the big question, you see a system of equations. So the question is, can 3, 1 be expressed as a linear combination let's put linear combo from now on, right, as a linear combo of the vectors 1, 1 and 1, 1. Now, as before, right, as with the last example, these are the same vectors, so really you don't need another 1, 1. So really the question is 3, 1 a linear combination of 1, 1, or is it a scalar multiple of 1, 1? And the answer is no. You can multiply 1, 1 by any number you want, and you're not going to get 3, 1. Right? Multiply it by 3, you'd get 3, 3. That's not 3, 1. Multiply it by 1. There's no way to multiply 1, 1 by a scalar and get 3, 1. All right, but we'll see that. Let me put a question mark there, and yeah, we'll see that the answer is no, meaning that this system's going to have no solution. All right, and we'll do that now. All right, let's try solving it. Again, this is one where I don't really need the calculator because it's a very, very simple one to put in reduced echelon form. Got 1, 1, bar 3, 1, 1, bar 1. And again, very easy, just doing this basically the same operation as the last example. I would take the opposite of row 1 entries, add them to the row 2 entries to give me new row 2 entries. Right? So reduced echelon form, reduced row echelon form, I got 1, 1, 3. And then, negative 1 plus 1, 0, negative 1 plus 1, 0, negative 3 plus 1, negative 2. And there's the problem, right? Yeah, you could talk about this is a pivot and x1's basic, x2 is free, but it doesn't even matter because look at this second row, what this corresponds to. This means that 0x1 plus 0x2, so 0 equals negative 2. This is a totally false statement. And if you boil down to, you try to solve a system and you end up with some totally false statement, something that can't be fixed, that means the system has no solution. Right? The system is what they call inconsistent. Right? When you have a solution, at least one that is consistent, this is inconsistent. Right? Means no solution. Right? So that's why we're answering no to that question. Right? Can 3, 1 be expressed as a linear combination of 1, 1 or a scalar multiple of 1, 1? The answer is no. So it says no solution. There's nothing more I can do with this. There's nothing I can fill in for x1 and x2 to make this a true statement. I'm done. All right. Great. Okay. Now we're bumping it up a bit to 3 equations and 3 variables, but it's the same concept. All right, and this is where I'll start using the calculator a little more. Same concept. If I want to write this system, express it as a linear combination, I'm going to have, x1 times the vector 1, negative 1, 2, right? Plus, and then x2 times the vector negative 2, 3, negative 5. Plus, and then x3 times the vector 3, 0, right? There is no x3 in the second equation, and then positive 5. Right, and these columns, right, these would be the columns of the coefficient matrix if I wrote that as a matrix equation, right? Equals, and then the constant vector on the other side, 9, negative 4, 17. All right, and so basically it's, now I'm not going to write the question this time, but when you see, you can always ask this question. When you see a system of linear equations, you think, can I write this vector, right, the vector with the constants, as a linear combination of the vector 1, -1, 2, -2, 3, -5, and 3, 0, 5. The coefficient, the column vectors with the coefficients of each variable. All right. Okay, and we'll see. All right, can we do this? So here's where I go into solving. Right. So again, just the augmented matrix with the coefficients of x1, the coefficients of x2, the coefficients of x3, a little bar for where the equal sign is, and then the constants. All right, and then like I said, I'm going to just go to the calculator. I'm going to put this in reduced row echelon form. All right, so again, back to the calculator, go to that matrix. Oh, let me turn it on. Right. So go to that matrix menu. Now I'm just going to stick to matrix A again. All right. And this is now, right, this is a 3-row, 4-column matrix. So it's a 3 by 4. And put all these entries. So 1, -2, 3, 9 for the first row, -1, 3, 0, and -4 for the second row, 2, -5, 5, and 17 for the third row. All right, and then I'll get out of here. All right, so quit, go back to the main screen. Now, the reason why I just used A again is because you see how it already has in the previous entry reduced row echelon form for matrix A. So I'm going to just enter that again. Instead of going back to the matrix in the math menu, I'm just going to go second entry. Above the enter sign, there's entry. That just puts in the last thing you typed. But now matrix A is this matrix, this 3 by 4 here from this problem. And there you go. All right, so here it is in reduced row echelon form with one, you got 1, 0, 0, 0, 1, 0, 0, 0, 1, a little bar. Again, they don't have the bar. Then they don't have the bar in the calculator. You're gonna have to remember where that is, where the equal signs are, and then 1, -1, 2. All right, so hey, look, this corresponds to a solution. First equation is x1 equals 1. That's it. Second equation is x2 equals -1, and the third equation is 1x3 equals 2. Here are the weights. And here's the solution of the system, or the weights of the linear combination, right? The coefficients of those vectors. All right, and then let's just double check. Now I think I entered everything correctly in my calculator, but let's just double check, make sure this is true. 1 plus 2 plus 6 would be 9, yes. -1 minus 3 would be -4, yes. 2 plus 5, right, when you put a -1 for x2, 2 plus 5 is 7, and then plus 10 is 17, yes. So this is in fact a good solution. Always check your solutions, please. Okay, and then let's write the linear combination, right? So how do I express 9, -4, 17 as a linear combination of these three vectors? Well, this way, right? So put in 1 for x1, so no need to write 1, just put 1, -1, 2 there. That's one of that. Then plus -1, but instead of plus -1, put -1, just minus. Right? Minus vector -2, 3, -5. And then plus x3, plus 2 times 3, 0, 5. And there you go. That linear combination of these three vectors gives me the 9, -4, 17 that I wanted. Okay. Wonderful. Good. All right. And again, what you're going to see is when there's only one solution, I'm just going to say this out loud because again, I said earlier, there's going to be a video later I put up about this. But yeah, when you see that when there's only one solution, usually that'll imply that the vectors, these column vectors, are what they call linearly independent. But we're not doing that here because you're going to see when we test for linear independence and dependence, the constant vector is the zero vector when we test for that stuff. So, I mean, they'll be independent. All right, if you have a system of equations like that and there's one solution, those column vectors are going to be linearly independent. Right? But again, enough about that. All right, so another one. So again, it's 3 equations, 3 variables again, and really you can ask this question, can 0, negative 1, 1, that vector, be written as a linear combination of 0, 1, negative 1, 1, 0, 3, and negative 1, negative 3, 0, right? Those 3 vectors. Can this, as a linear combination, I have x1 times the vector 0, 1, negative 1, right? Just the coefficients of x1 going down. Plus x2 times, and then again the coefficients of x2 going down, 1, 0, 3, plus, and then x3 times the vector, with the coefficients of x3, negative 1, negative 3, and 0. And again, these would be the columns, right? These 3 would be the columns of the coefficient matrix if you wrote it as a matrix equation. And then we have equal to, the constant vector on the other side, 0, negative 1, 1. All right, so let's see if this can happen, right? Does this have any solutions? Are there any weights, x1, x2, x3, that I can put in for this? All right, so let's solve. I'll write the augmented matrix. So 0, 1, negative 1, 1, 0, 3, negative 1, negative 3, 0, little bar where the equal sign goes, and 0, negative 1, 1. Now you may already be saying, hey, isn't this vector just negative 1 times this vector? Well, yeah, it is. So what we're going to see here is that there is actually no need to have these two. So if these two end up adding up to nothing, we can put negative 1 here. Now there might be infinitely many solutions here. There might be just one where this is negative 1, these two are 0, but let's see what happens. All right, so back to this. All right, so again, I'll just change matrix A and re-enter this. So matrix, over to edit again, 3 by 4, and still a 3 by 4, and then just enter these new entries. All right, so 0, 1, negative 1, 0. There's the first row. 1, 0, negative 3, negative 1, sorry, second row, then negative 1, 3, 0, and 1. All right, then I get out of this, do the entry thing again, just because I already have reduced row echelon form up there. And okay, now I'll write this down. All right, so putting this into reduced row echelon form. 1, 0, negative 3, negative 1. Then 0, 1, negative 1, 0, and 0, 0, 0, 0. Okay, so last row corresponds to 0 equals 0. That's all right. Remember, that's fine. You can ignore that. That's always true. So this is another one of those where, you know, the first column is a pivot column. So x1 is free. Is basic. The basic. The second column has a pivot, right? The first non-zero entry is a 1 in the second column. So x2 is basic as well. It's this third column that doesn't have a pivot, doesn't have one of these leading ones in any of the rows. So x3 is free, meaning I can let x3, the value of x3, be anything I want, any real number. All right, now because x3 is free, I'm going to replace it with something. Okay, again, I know you can leave it as x3 if you wish. That's totally fine. I just like using other letters to avoid confusion in the future. So I'm going to let x3 be, again, just t, right, where t is any real number. Right, again, it doesn't have to be t. It can be any expression you want that can take on any real number. T, s, 3t, 5t, 1/5 t, t plus 5. Right. Just you can let the free variable be replaced by an expression that represents or that can take on any real number. All right. So hopefully you can see that from this first equation, you have x1 and then minus 3x3. But remember, I'm calling x3 t. So x1 minus 3t equals negative 1. So we're getting the value of x1 is, negative 1 plus 3t. Or 3t minus 1, same thing. And then from the second row, I have x2, 1x2, and then minus x3, right? Minus 1x3. But again, I'm letting x3 be replaced by t here. So minus t equals 0, leading me to the fact that x2 will be equal to x3, or x2 will be equal to t as well, right? Whatever I choose for t. But there are infinitely many solutions here. And as I was saying earlier, when there are infinitely many solutions, that means at least one of these columns isn't necessary, right? And again, we'll go into do a video later. I've said this a bunch already, where I talk about how to determine, which vectors are unnecessary, right, for the linear combination. All right. So the solutions of this system are going to be in this, there's an x1, there's an x2, there's an x3. But I'm, writing each of them in terms of this free variable x3, which I called t. Right? I replaced it with t. So yeah, x1 is again, negative 1 plus 3t, or 3t minus 1 if you want. x2 is t, and x3 I said was this value t as well. All right, and again, t is any real number. All right. So remember how earlier I was like, hey, I don't need x2 and x3. I don't need these two, because I can just multiply the first vector by negative 1 and get what I want. So when t equals 0, right, when t equals 0, I get one solution where x1 is negative 1, like I said. All right, x2 is 0, and x3 is 0. All right, and then back to our linear combination statement here. And then double check, would this be true back in the original system? 0 minus 0 is 0. Negative 1 minus 0 is negative 1. And 1 plus 0 is 1. It works, right? This is a good solution. But then we get our linear combination of, negative 1 times 0, 1, negative 1. plus, 0 of the other stuff, right? And again, there's no real reason to write 0 times something. You can just not write it, but I'm going to. Okay, so there's one way to write this. 0, -1, 1 is a linear combination of these three vectors, right, where the weights are -1, 0, and 0. But you can do anything you want. Just replace t with any number you wish. What if t were, I don't know, -3? Doesn't matter, right? Let t be any real number. Well, then the weights of the linear combination x1, x2, x3, x1 would be 8. Nope, sorry. -10. -1 plus -9, so -10. x2 would be -3, and x3 would be -3. All right, and then our linear combination would be -10 times the first vector, right, times 0, 1, -1, -3 times the second vector, 1, 0, 3, and -3 times the third vector, -1, -3, 0. That should be equal to 0, -1, 1. You can double check, right? Let's see, you'd have 0 and then -3 plus 3 would be 0. -10 plus nothing, and then plus 9 would be -1. And then +10 minus 9 would be 1, and then plus 0 is 1. Right, this works. And you could do this forever, right? You could do this as many times as you wish. There's infinitely many solutions. Just pick different values of the free variable. Pick different values of the parameter t. Right? Replace t with anything, and you get a different linear combination. Okay. All right. Got a couple more. All right, notice how they're all the same. Right? They're all pretty much the same. So here's another one. So again, I'm going to write it as a linear combination statement. Again, you could do a matrix equation if you want, with the coefficient matrix times the variable matrix equals a constant matrix. But this is, x1 times the 3 by 1, 1, 2, 1, plus x2 times, and then its coefficients in a vector in a column matrix, -3, -1, 2, plus x3 times its coefficients in a column matrix, 1, -2, -3, equals, and then 1, 2, -1. All right. So again, the question, whenever you see a system of equations, the question can be, can I write this vector, right, 1, 2, -1, as a linear combination of the column vectors with the coefficients, right, of 1, 2, 1, -3, -1, 2, and 1, -2, -3. So, does this have a solution or not? Can I find weights x1, x2, x3 that would make this true? All right, so let's go into solving it. So I'm going to again write the augmented matrix. 1, 2, 1, -3, -1, 2, 1, -2, -3. Little bar where the equals would go. 1, 2, -1. All right, and then as I've been doing, like I said, I don't want to. You can do the elementary row operations, right? If you're asked to use Gauss-Jordan elimination, you should use row operations, show it step by step to get it in reduced echelon form, reduced row echelon form. But I'm going to go again back here to the calculator matrix, go over to matrix A again, edit. It's still a 3 by 4, and then enter these. First row 1, -3, 1, 1, then 2, -1, -2, 2, then 1, 2, -3, negative 1. Great. All right, so I get out of here. And I've already got, the last entry was again reduced row echelon form, so let's go to second entry. And here we go. And if you have the decimals are fine. If you want, you can change it to a fraction by hitting the math button. And the first thing is change to frac, right? And it takes the previous answer, changes everything to fractions if you like fractions better. Okay. So we have 1, 0, -7/5, and then 0. And then 0, 1, -4/5, 0, and 0, 0, 0, 1. Uh-oh. Right? So it's like, oh yeah, x1 is basic, x2 is basic, x3 is free. It doesn't even matter. None of that matters, because look at the last row. That corresponds to 0. 0 equals 1. Something that is never going to change, always false. You can't fix it. So that implies that the system is inconsistent, has no solution. So there is no way to write this vector as a linear combination of these three column vectors. Okay, that's it. I'm done with that one. All right, it's that simple. When you realize that there's no solution, you stop. Can't write that constant vector as a linear combination of the column vectors of the coefficient matrix. All right, now so far we've seen a bunch of examples. Now where there's the same number of equations as variables, right? There's been 3 equations, 3 variables, 2 equations, 2 variables. The reason I wanted to put this example up, this last one, because there are more equations than there are variables, right? There's 3 equations, 2 variables. And you could look at other ones where there's more variables than equations, but those ones are a little simpler because the calculator works for them. I wanted to show you this one because I wanted to show you how to work with the calculator on a problem like this. So again, you can still, you can set it up as a coefficient matrix times a variable matrix equals a constant matrix, totally fine. But again, you can write this as a linear combination statement as well. Right, so I have x1 times, and then its coefficients down here, a 3 by 1 matrix vector, -3, 3, 4, plus, and then x2 times, and then its coefficients in a 3 by 1 vector matrix, 5, 4, -8, equals, and then another 3 by 1 on the other side, -22, 4, 32, right? So the question here is, can I write this vector as a linear combination of these two? Right, and these are in R3, right? These are in 3-dimensional space. They have 3 components. And if it has 2 components, it's in R2, whatever. All right. So same thing I've set up. I'm going to solve it. Right? Try solving the system same way I've been doing everything. A little augmented matrix. Coefficients of x1, coefficients of x2, and then the constants. A little bar for where the equal signs are, then the constants. Oh. All right, I guess this one won't be so bad. This is a 3 by 3 matrix, and the calculator does put a 3 by 3 in reduced row echelon form. All right, I apologize. I meant to put up I should have looked at it more. I looked at it harder. So I go to the matrix here. All right, go over to matrix A. And I'll do this one. And I wanted to show you something on the calculator, though, all right, when I'm done with this. All right, so this is a 3 by 3. First row, -3, 5, -22. And then second row, 3, 4, 4. Third row, 4, -8, and 32. Okay. Now, I can't do that entry thing again because now it'll change to fraction. That's the last thing. So I have to go back to the matrix if I want to do the, go over to math and then go down to that RREF again. And then enter the name of the matrix. Second matrix A and enter. Okay. So it does 3 by 3s. Right, it does 3 by 3s. So this in reduced row echelon form, that's an F, is the 3 by 3. You got 1, 0, and again where the bar is here is after the second column, 4, 0, 1, negative 2, and then 0, 0, 0. And again, that last row is fine. All right, this implies that 0 equals 0, but that's a true statement. You can ignore that. That's always fine. So there is a solution here, right? We get from the first row x1 equals 4. All right, 1x1 plus 0x2 equals 4. And then from the second row, we're getting x2 equals negative 2. So there is a solution. You can write this vector as a linear combination of these two, and here is how. 4 times that first vector, negative 3, 3, 4, and then plus, replace x2 with negative 2, minus 2 times the second vector, 5, 4, negative 8 will be equal to, and then we'll double check this, negative 22, 4, 32. And let's see, that'd be a negative 12 minus 10 is negative 22, yes. Then the second component, you'd have 12 minus 8 is 4, yes. Then the third component, 16 plus 16 is 32. Fantastic. All right, so here it is, the linear combination. All right, now what I was hoping for, I apologize. Let me go back to this matrix menu in the calculator here. All right. Now, if I go over to edit, what I want to do is show you what happens. Now, when the rows and columns are equal, or when the rows is less than the number of columns, you're fine when you want to go and put it in reduced row echelon form. It's when the number of rows is greater than a number of columns. All right, so I'm going to go here, and I'll enter some random fourth row, just 1, 2, 3. All right. So now you see my matrix A is, the number of rows is greater than the number of columns. So that means the number of equations is, greater than the number of variables. There'd be 4 equations, 2 variables here, if I was, corresponding this to a system. Now, when I get out of here and try to do reduced row echelon form, look at what happens. See, it says invalid dimensions. All right. Now, that doesn't mean you can't put it in reduced row echelon form. All right. You can put any matrix into reduced row echelon form by hand. All right. It's not impossible. It's always, just get those lead ones with zeros above and below them, and then you got it, right? So you can put any matrix you want into reduced row echelon form by hand. Just for some reason, and I don't know why this is, on a calculator it doesn't do it when the number of rows is more than the number of columns. So I have a very quick way to fix that. All right, so it says error. Easy way to fix that. Go to the matrix, and if you end up trying, if you're trying to put a matrix with more rows than columns in reduced row echelon form, just increase the number of columns so that they're equal. So this is a 4 by 3. I'm going to make it a 4 by 4. All right, and that'll add on. You see, when I move the cursor over, that'll add on another column of all zeros. Leave it. Just leave it as zeros. Because when you do row operations, when you add rows to other rows or multiply rows by a scalar or switch rows, a column of zeros will not change. So no matter what you do row operation wise, if you were doing this by hand and you had a bunch of zeros down one column, that would always be a bunch of zeros. Nothing will change. So then the 4 by 3 matrix, all the other entries, all right, these guys here in the 4 by 3 matrix, I can now put this in reduced row echelon form, right? And just ignore that column of zeros. So now I get out of here and do the same thing, put reduced row echelon form, and it'll do it. And just ignore the column of zeros, and this 4 by 3, the 1 0 0 0 1 0 0 0 1 0 0 0, that would be the 4x3 matrix earlier put in reduced row echelon form. All right, so again, for some reason, when there's more rows than columns, just add a bunch of columns of zeros until the number of rows and columns are equal, and then ignore them. And you can have the calculator put your original matrix with the more rows than columns into reduced row echelon form. All right, so that is all I've got for you today for this video. Turn it off. All right. And just, yeah, okay, so you can take any system you wish, right? Any system of linear equations you can write as a matrix equation, and then solve it, finding an inverse if there is one, if it's a square matrix. You can set up an augmented matrix, like I've been doing, solve it that way, or put it in reduced row echelon form using Gauss short-on elimination or your calculator. And you can write them as linear combinations, and then express the and you're going to be asking the question, can I express the constant vector, right, the constant matrix, as a linear combination of the columns of the coefficient matrix? All right. And that's it. All right. Thank you very much for watching.